Okay, our final speaker of the morning session is Leonid Chekhov. He's talking about symplectic groupoid, geometry, networks, and noncommutativity.
Thank you for this invitation to this great conference. And I'm about to talk about some models that occupy, well, my mind for the last probably 25 or 30 years. And it's based on my joint papers with Misha Shapiro and many more. And meanwhile, usually Shapiro that was mentioned today was Sasha Shapiro, his son. But Sasha Shapiro will appear in my talk as well. So actually we have many Shapiros. Okay, so let me start with the introduction. Let me immediately start with what we call by Alexei Apre and Alexei Bondel. So Bondel's symplectic groupoid. And I will try to explain why this object has some importance related to geometry. So consider A. A will be a set of unipotent upper triangular matrices. And the definition of the groupoid definition is that we have a pairs of matrices that we call compatible pairs, such that B is some matrix, well, from SLN in general, and A is from this set of upper triangular matrices, and the condition is such that if we consider this matrix product, then this combination itself is a unipotent upper triangle. And for example, would it be just a joint action, then the solution will be trivial, right? So take just all matrices upper triangular and it will provide the answer. But because we have this transposition and it's actually reflects the fact that A is not interpreted as an operator in some basis. It's more like two form. So it's a transformation related to the forms when we change the basis using the matrix B. So it immediately makes this condition non-trivial. Let me present some example. For instance, if I have what is an example of a compatible pair? Let's take A to be in 3 by 3 case. So it will be my main case today. And B, well, one example is just take B to be well, then if we do this multiplication, would I present it to students? I will do it explicitly, but we can just skip this part and just everyone can check that the result of this operation will be again upper triangular matrix of this form. So for instance, these two matrices, they actually constitute a compatible pair. Why it's groupoid? So groupoid means, of course, that we have a structure. So, and the structure consists of several maps. So we have just from the general theory of symplectic groupoids by So again, it's so this is a construction due to Bondel, but general theory was developed by Karashev and Weinstein. Around 87, 89, 88. So we have a source map from this compatible pair into A. We have a target map into the resulting transformation. We have injection, which, well, I will. So if B is unitary, is unit matrix, then it's always compatible. We have inversion. Again, so it's so this transformation is invertible. And finally, we have a natural multiplication. So if we have two pairs where we have two compatible pairs where source of one pair coincides with the target of another, then we may make a composition and just get that it's. So why I write it? Because it's more or less clear. Because we have also, so and there is a natural projections. Natural projections from this product of two compatible pairs. One is projection to the first component. Another projection is to the second component. So it's just BA. What is non-trivial is, so far it's just pretty much general and not so maybe interesting. Non-trivial part is that we have, if we have this pair with two projections, then we can make transformation by source and target map, and this diagram is commutative. Commutative, and moreover, there exists a general symplectic structure. Split symplectic structure such that it splits on the level of these two projections. And actually it's a non-trivial statement because, for instance, this actually implies one, there are many implications, but one of implications of this is that, for instance, it implies that source and target maps Poisson commute with respect to this symplectic structure. So then it was Bondel was able to solve the corresponding algebraic problem when B is actually in the vicinity of the unity matrix. When G is small, so to speak, then I will skip this part, and just to say that again, using this projection to the set of upper triangular matrices and this identity map, we are able to restrict the corresponding symplectic or Poisson structure just to the set of upper triangular matrices themselves. And what we obtain, we get the Poisson relation, which almost the one that we have so many times already on this conference, except that it's slightly different from what we had before. R is just the same. So I write it in semi-classical case, but it can be also written in quantum case. So R is a semi-classical R matrix, so it's some theta I minus j, eij cross e ji, where theta is 1 theta of x. It's 1 for positive, half for 0, and 0 for negative arguments. So what is in, and T1 is a partial transposition. So it's exactly the formula that is on the cover page of Alexander Molev's textbook on the twisted Youngians. And, well, in quantum case, I'm sorry. So, but what is interesting? Because the interesting part is that the same structures appear and very well known in geometry. And this is the same as what is called a Goldman bracket. Goldman bracket on a particular set of geodesic functions. So let me just say a couple of words about that. So consider a Riemann surface, sigma gs, where G is the genus, can be arbitrary, and S will take equal 1 or 2 is a number of punctures. A Goldman bracket can be defined for any Riemann surface. It's just that, and we consider this Riemann surface as obtained in the Poincaré uniformization, where delta GS is a Fuchsian group. Fuchsian group is some discretely acting subgroup of PSL2R. So in this picture, we have something that we call the geodesic functions, which are related to hyperbolic cosines of actual lengths of the geodesics. And if we have, for instance, if we have this, one of my main examples will be, say, a torus with one hole. And we have infinitely many, of course, of these geodesic curves, closed geodesics. But let's consider a situation when we have two curves and they have a single intersection. Then this single intersection can be resolved in two ways. So if I have this, then I can write that it's one resolution is when we just make it surgery this way. The other one, we do it differently. And in both cases, we observe that we obtain a single geodesic. after this operation. So here we have two, G1 and G2. And here I have just one, how did I? Let's call it GI and GH. And we have two relations between these between these four geodesic functions. First is what is called just a purely classical skein relation. So if we just take the product of these two, is the sum of these two geodesic functions. This just is easy. It just follows from some trivial relations for SL2 matrices. So it's a skein. What is less trivial is a Goldman bracket. So if we have a Poisson bracket between them, then we can write it as a corresponding difference. And this enables us to actually close, so these two relations is enough to close the corresponding algebra. How we can, for instance, I want to express a bracket between these two geodesics in terms of just one geodesic in this right-hand side. So just let me do it here. So we have that correspondingly well, we have G1, so we have these two relations, and I can use the screen bracket to express one of these. And we have, for instance, that we have 1/2 G1 G2 minus GH, and all this G3. And then we can check, for instance, that actually this algebra is closed on the set of these three geodesic functions. And surprise is that the corresponding algebra is actually the same as this algebra of twisted Yangians. And even more, with Volodya-Fock, we were able to obtain the realization of this algebra in the general for the general N. So it's something that, well, now I can open some small secret that is hidden here. We come to this picture soon. But before that, so again, so this algebra has really many names. Probably the first were Gavrilik and Klimik, but then there was Dubrovin, Ugaglia, Nelson, Jeanette Nelson, Regge, well, Bondel, and well, I'm running out of space. Maybe I have to add some more names, but just to mention that this algebra appears in many discrete ways. And with Volodya-Fock, we were able to find the fat graph description or fat graph representation in our paper of 2000. Namely, so if we consider the fat graph that is representing the corresponding surface, I have to, of course, skip a lot of details just to draw this graph. So it's technically easier to draw it in this strange way, so because otherwise it's oriented. It's just that I have to, if I want to make it orientable, I have to rotate it, so it will be very screwed graph, very much non-planar. And in this graph, for each, there is a very simple combinatorial description how we can associate some product of 2 by 2 matrices with the corresponding geodesic function that is represented by a closed path in this graph. But just to mention that if I consider this, so you see that for, so this is the case of n equal 5. So I have these 5 wrangles, 5 vertical wrangles. So if I take the geodesic function that goes through i's and j's wrangle, vertical wrangle, then this geodesic function can be associated with matrix element of the, well, in this case, 5 by 5 matrix, which is, so it's 2, 4, so it's element 2, 4. And, well, something that we were able, so it's actually quite easy to show that the corresponding geodesic functions, after we apply the skein and golden bracket, they actually produce the corresponding equations that we usually call, well, from integrable systems, we usually call it reflection equation. So this was the first preliminary part. The second preliminary part that I have to also mention is that we also have a natural braid group action. Braid group action, if we take a very special choice of the corresponding B matrix, so it's almost, so it's unit matrix except that 2 by 2 block. Then the first is that this matrix is compatible. So it's actually matrix from the corresponding symplectic groupoid. And second, that this transformation is actually on a geometrical level correspond to the den twist along, so it's A, let it be G, along the corresponding geodesic on the Riemann surface. So just to convince you that this object has some rights of existence and is interesting, and what was not much known or not known at all, or at least not known to myself for many years, there were 2 problems. First, well, if you just compare the dimensions of the corresponding spaces, so dimension of this space A obviously is n minus 1 by 2, and dimension of the corresponding Riemann surface, so genus is actually integer part of n by 2, s is 1 or 2, so the dimension of the corresponding is 6g, so real dimension, 6g minus 6 plus 3s. And obviously it increases as a linear function in n, and this increases quadratic function. So also for n equals 3 and 4, geometric leaves are are the corresponding Poisson leaves of maximum dimension, so generic leaves. Huh? Well, it happened. We have actually S central elements here. So we have, or maybe no. Okay, so let's make it 2. It's easier. I think you're right. That's I don't remember by heart, but yeah. So there. Let's see. So for G, no, it's 3. It's 3. Sorry. For genus 1, it must be 3. For genus 1 and S equal 1, it must be 3. For yeah, then the next is 6. Also for n equal 4, it's 6. So no, it's 3s. Real, yeah. Everything is real. Everything on my talk today is real. Okay, so the first question that we have is that so find the canonical variables for non-geometric leaves or generic leaves. And second, just to solve the groupoid condition and find the corresponding parameterization or coordinatization of the symplectic groupoid itself. The first problem, I think, was solved in my paper with Misha Shapiro at 2000, and this one actually was solved in 2003, and I will just explain the solution to both these problems simultaneously. So for this, we just switch the topic and come to what we call networks. And not surprisingly, cluster algebras. So here is one example of the network. So in blue, I actually represent the cluster variables. And what we have here, it's already appear, is actually two. Sorry, it's probably better to draw it this way. So there are two triangular networks of Fock, Goncharov, Schoen type. But actually, we can consider any planar network. So imagine that we have any planar network. Most of this you see So we need only the planarity condition. And we can define what we call a transport matrix. So this network, you see, has some natural sources and natural sinks on the boundary. And we just define, first of all, we have these variables. So we defined if I have any path from G to I, so here is drawn in red, one of possible passes. Then to this path we set into the corresponding the weight. That is a product of all cluster variables that lies to, well, to the right. And actually, we can easily upgrade this definition to the quantum version if we just, again, set something that we call normal, or while ordering that already appears in the previous talk. So we can define it in quantum case as well. Then the transport matrix, element of transport matrix, so it's somehow, so J enumerate columns, so Tij is just the sum over all passes from G, from the source to sink, weighted by the corresponding weight. So this sum, if the network is acyclic, then this sum is a polynomial. But the same works for a cyclic network, then it's just a rational function. So what was the result of Gehman, Shapiro, and Weinstein? So it's different. It's Alec Weinstein, not the Weinstein. Weinstein. So it's even different. It's even different letter. And so the result from 2010 is that any such planar network satisfies the classical or quantum Lie-Poisson equation, so even written also in the quantum case. So it's very general. It just happened for any planar network. What is very much specific, however, to this Fogg-Goncharov, and meanwhile this immediately implies something, namely that if we have some rectangular network with two transport matrices, so it has, let it has n sources and 2n and 2n sinks, like this, or like just in the standard triangular Fogg-Goncharov chain, then the claim that if we just define A to be T1 transpose T2, this matrix satisfies this equation, let's call it, because it has different names. So this simple construction immediately solves problem number 1. So having any such planar network, we can produce a solution to this twisted Yangian or reflection equation. But what is very much specific for this Fogg-Goncharov chain is that besides this condition that is very general, we have one very special condition. So if we have Fogg-Goncharov chain, so triangular, so I will not draw it, so it's just, for instance, everyone can just imagine that it's just half of this, with the addition of the corresponding lines between these Froden variables. And we define 3 transport matrices from this side to that side, from this side to that, and from this to that. Meanwhile, all these transform matrices are upper or lower triangular, depending on the direction. So in opposite direction, it will be lower triangular. So all of these, for instance, are upper triangular. Then we have and define them to be, so I will use the same letter. It's intentionally T1, just differ them by some sign. So then, so if we introduce the matrix S, that is a matrix of inverting the flag at the corresponding vertex, then we have this interesting relation. So I have to write them in proper order. So this is something that we call the path groupoid condition. And using this path groupoid condition, we actually can parameterize the corresponding matrices A and B in the compatible pair. So this is the next theorem. So if we just represent B, so especially in this case, it's easy. So actually B is a transport matrix from this left side to this right side. So if I draw it in this picture, then I have 2 transport matrices. And if we say B is given by just this matrix product T1, T2, so one is lower triangular, another is upper triangular, and A is, let me be, T2. So I will just draw so the missing parts. So this transport matrix T2 bar, here is T2 twiddle, and here is as before T1 bar and T1 twiddle. So we have 6 transport matrices, but they satisfy 2 path groupoid relations. So if we represent B in this form and A in that form, then B transpose is an upper triangular matrix, and it is given by, again, so it's explicit matrix product. T2 transposed. So it really solves the corresponding groupoid condition, and moreover, we can, the corollary is that these matrices A, B, and A twiddle that we use this for denoting this target map, they satisfy closed Poisson algebra, or, well, we can also upgrade it to the quantum algebra. Yeah. So what is the outcome? There are several, to be honest. The first outcome that, and maybe one of the most interesting related to geometry, is that consider on this. Consider again, let's come back to this picture. And just try to interpret the corresponding quantity. So we say that, for instance, consider example n equals 3. Then we say, okay, these elements of this matrix A, original matrix A, they describe some geodesic functions, like it was before. And the third one, so it's closed. And but what is the interpretation of the elements of this A-twiddle? First of all, they share the same central element. And the central element is something that we call a Markov element, namely it's I13 minus squares. And in geometry, it corresponds to the perimeter of the hole. So then, and it is the same for A and A-twiddle. So actually, we can interpret this A-twiddle as geodesic functions for this lower part of the same Riemann surface. Now just a closed Riemann surface of genus 2. And what we were missing all these years, we were missing for this missed link. So the geodesic, let's actually connect these two parts. That was never in triangulations. But it happens that we nevertheless can define this in this picture, in this algebraic picture. And this is my last statement, last theorem that I will be able to present. Oops. So, so I will present this statement for genus 2, but, well, there are some issues with higher genus, but that's something that I will not be able to describe. But for genus 2, it is a theorem. So consider the Teichmüller space of closed Riemann surfaces of genus 2. Then it's parameterized by cluster variables. Cluster variables, there are 7 of them. By some technical reason, we have to add one extra vertex with the condition that E square A, B, C, D, F, G equal 1. And one of possibilities of drawing this quiver is a quiver of exceptional X7 in this quiver classification. So it's E, let me, so G, F, G, A, and B, C. And with the geodesic functions G1, 2 equals, so I explained. So it's also related to these telescopic sums that were mentioned. G 2, 3 is a telescopic sum of this form, GB is GF, G 2, 3. And finally, G12 is BC, where by definition, and then we have this telescoping sum. All these geodesic functions, so we need 5 of them, and we need the skein and Poisson relation to get all actually closed geodesics on this surface. Moreover, all Gij are elements of upper cluster algebra. Elements of upper cluster algebra means that they, so this means that they belong to the positive definite polynomials of, in general, half integer powers of cluster variables in any cluster, in any seat. Okay, and I will not be able to mention non-commutative case, unfortunately, but okay. But what I probably have to mention that if you refrain from this condition and say replace this by some h bar, then what was done in our paper with myself, then M Shapiro, A Shapiro, Gus Schrader, Semyon Artamonov, Francesco, Paolo Di Francesco, and Renat Kidem is at the same query with the same set of functions gives us the description of that's what I never remember. Semyon is not here, right? Yes, how it's elliptic. It's okay. So elliptic. And just to mention that we have the similar constructions for any n. So it's not that we, so for in cluster variables, construction for any n are well defined. It's just that to relate them to geometry, we again need to make some Hamiltonian reduction, which hinders the progress. We want to make the exam for genus 3, and it's actually very stubborn. So we are struggling for the last year with this example. But it will be done, and then, well, I hope that it will can be formulated for any genus. So that's it. Thank you so much for your attention.
Thanks, Leonid. Questions?
I suppose this realization for the symplectic groupoid exists on the classical level. Do you know its geometrical meaning?
What do you mean by no? So if you remove this condition,
No, just the theorem. The the realization.
No,
symplectic
it's like,
groupoid.
no. It's we can define this GB for any n. It's just that it's too big. It's because we again encounter the same trouble that we have here, except that now we know this. We know this realization of the higher of the general symplectic leaf, but we need to collapse it to the geometric symplectic leaf. If this is what you are asking, so
Not
Dima.
exactly, but we will discuss it later.
Okay.
More questions?
The underlying object for your Poisson bracket star is the orthogonal algebra. So my question is, how far can you go if you replace it with the symplectic algebra?
Well, no, for this, but that basically was in the previous talks, right? When we, for symplectic, you mean symplectic when we just have not partial transposed here, right? That just was in this, actually in the previous talk, right? By Emil. So it's then the transposition. We have just then somehow replaced this by something besides the transposition, right? So first of all, I believe it can be done, Sasha. Second, actually, this transposition is some mysterious operation, to be honest. It's more mysterious than inversion. Because, for instance, what it produced from this quiver, you see, from this quiver, it produced this one, which is not quite obvious how it can be done. Which, of course, I have to skip this part, but just to mention that this transposition, for instance, makes this picture immediately non-planar. Again, I have to remove technical parts, but the appeared quivers, they are non-planar. And I think that in this case that you mentioned, that was presented again by they're still planar, the corresponding quivers. So there is some small details, but that make a lot of difference.
More questions? Okay, I wonder who beat the record in the number of authors in the papers.
What?
Was 7 people in the paper. I think you have the record for today. Okay, dismissed. Lunch break.